Squaring the circle is a problem proposed by ancient geometers. It is the challenge of constructing a square with the same area as a given circle by using only a finite number of steps with compass and straightedge. More abstractly and more precisely, it may be taken to ask whether specified axioms of Euclidean geometry concerning the existence of lines and circles entail the existence of such a square. In 1882, the task was proven to be impossible, as a consequence of the Lindemann-Weierstrass theorem, which proves that pi is a transcendental, rather than an algebraic irrational number. That is, it is not the root of any polynomial with rational coefficients. It had been known for some decades before then that the construction would be impossible if pi were transcendental, but pi was not proven transcendental until 1882. Approximate squaring to any given non-perfect accuracy, in contrast, is possible in a finite number of steps, since there are rational numbers arbitrarily close to I0. The expression squaring the circle is sometimes used as a metaphor for trying to do the impossible. The term quadrature of the circle is sometimes used to mean the same thing as squaring the circle, but it may also refer to approximate or numerical methods for finding the area of a circle. History: methods to approximate the area of a given circle with a square were known already to Babylonian mathematicians. The Egyptian Rhind papyrus of 1800 BC gives the area of a circle as d2, where d is the diameter of the circle, and pi approximated to 256/81, a number that appears in the older Moscow mathematical papyrus and used for volume approximations. Indian mathematicians also found an approximate method, though less accurate, documented in the Sulbas Sutras. Archimedes showed that the value of pi lay between 3 + 1/7 and 3 + 10^71. See numerical approximations of I0 for more on the history. The first known Greek to be associated with the problem was Anaxagoras, who worked on it while in prison. Hippocrates of Chios squared certain lunes, in the hope that it would lead to a solution C lune of Hippocrates. Antiphon the sophist believed that inscribing regular polygons within a circle and doubling the number of sides will eventually fill up the area of the circle, and since a polygon can be squared, it means the circle can be squared. Even then there were skeptics. Eudemus argued that magnitudes cannot be divided up without limit, so the area of the circle will never be used up. The problem was even mentioned in Aristophanes' play The Birds. It is believed that Oenopides was the first Greek who required a plane solution. James Gregory attempted a proof of its impossibility in Vera Circuli Hyperbolo Quadratura in 1667. Although his proof was faulty, it was the first paper to attempt to solve the problem using algebraic properties of pi. It was not until 1882 that Ferdinand von Lindemann rigorously proved its impossibility. The famous Victorian-age mathematician, logician and author, Charles Lutwidge Dodgson also expressed interest in debunking illogical circle squaring theories. In one of his diary entries for 1855, Dodgson listed books he hoped to write, including one called Plain Facts for Circle Squarers. In the introduction to A New Theory of Parallels, Dodgson recounted an attempt to demonstrate logical errors to a couple of circle squarers, stating, "The first of these two misguided visionaries filled me with a great ambition to do a feat I have never heard of as accomplished by man, namely to convince a circle squarer of his error. The value my friend selected for pi was 3.2. The enormous error tempted me with the idea that it could be easily demonstrated to be an error. More than a score of letters were interchanged before I became sadly convinced that I had no chance." Perhaps the most famous and effective ridiculing of circle squaring appears in Augustus de Morgan's A Budget of Paradoxes, published posthumously by his widow in 1872. Originally published as a series of articles in the Athenaeum, he was revising them for publication at the time of his death. Circle squaring was very popular in the 19th century, but hardly anyone indulges in it today, and it is believed that De Morgan's work helped bring this about. Impossibility: the solution of the problem of squaring the circle by compass and straightedge demands construction of the number, and the impossibility of this undertaking follows from the fact that pi is a transcendental number. If the problem of the quadrature of the circle is solved using only compass and straightedge, then an algebraic value of pi would be found, which is impossible. Johann Heinrich Lambert conjectured that pi was transcendental in 1768 in the same paper in which he proved its irrationality, even before the existence of transcendental numbers was proven. It was not until 1882 that Ferdinand von Lindemann proved its transcendence. The transcendence of pi implies the impossibility of exactly circling the square, as well as of squaring the circle. It is possible to construct a square with an area arbitrarily close to that of a given circle. If a rational number is used as an approximation of pi, then squaring the circle becomes possible, depending on the values chosen. However, this is only an approximation and does not meet the constraints of the ancient rules for solving the problem. Several mathematicians have demonstrated workable procedures based on a variety of approximations. Bending the rules by allowing an infinite number of compass and straightedge operations or by performing the operations on certain non-Euclidean spaces also makes squaring the circle possible. For example, although the circle cannot be squared in Euclidean space, it can be in Gauss-Bolyer-Lebesgue space. Indeed, even the preceding phrase is over-optimistic. There are no squares as such in the hyperbolic plane, although there are regular quadrilaterals, meaning quadrilaterals with all sides congruent and all angles congruent. There exist, in the hyperbolic plane, infinitely many pairs of constructible circles and constructible regular quadrilaterals of equal area. However, there is no method for starting with a regular quadrilateral and constructing the circle of equal area, and there is no method for starting with a circle and constructing a regular quadrilateral of equal area. Modern approximative constructions, though squaring the circle is an impossible problem using only compass and straightedge, approximations to squaring the circle can be given by constructing lengths close to pi. It takes only minimal knowledge of elementary geometry to convert any given rational approximation of pi into a corresponding compass and straightedge construction, but constructions made in this way tend to be very long-winded in comparison to the accuracy they achieve. After the exact problem was proven unsolvable, some mathematicians applied their ingenuity to finding elegant approximations to squaring the circle, defined roughly and informally as constructions that are particularly simple among other imaginable constructions that give similar precision. Among the modern approximate constructions was one by E. W. Hobson in 1913. This was a fairly accurate construction which was based on constructing the approximate value of 3.14164079. Which is accurate to 4 decimals. Indian mathematician Srinivasa Ramanujan in 1913, C. D. Olds in 1963, Martin Gardner in 1966, and Benjamin Bold in 1982 all gave geometric constructions for which is accurate to 6 decimal places of pi. Srinivasa Ramanujan in 1914 gave a ruler and compass construction which was equivalent to taking the approximate value for pi to be giving a remarkable 8 decimal places of pi. In 1991, Robert Dixon gave constructions for Koszalski's approximation, though these were only accurate to 4 decimal places of pi. Another example of a modern squaring the circle. 7 decimal places are equal to those of squaring or quadrature as integration. The problem of finding the area under a curve, known as integration in calculus, or quadrature in numerical analysis, was known as squaring before the invention of calculus. Since the techniques of calculus were unknown, it was generally presumed that a squaring should be done via geometric constructions, that is, by compass and straightedge. For example, Newton wrote to Oldenburg in 1676, "I believe M. Leibniz will not dislike the theorem towards the beginning of my letter Pag. For squaring curved lines geometrically." After Newton and Leibniz invented calculus, they still referred to this integration problem as squaring a curve. Claims of circle squaring equals connection with the longitude problem equals the mathematical proof that the quadrature of the circle is impossible using only compass and straightedge has not proved to be a hindrance to the many people who have invested years in this problem anyway. Having squared the circle is a famous crank assertion. In his old age, the English philosopher Thomas Hobbes convinced himself that he had succeeded in squaring the circle. During the 18th and 19th century, The notion that the problem of squaring the circle was somehow related to the longitude problem seems to have become prevalent among would-be circle squarers. Using cyclometer for circle squarer, Augustus de Morgan wrote in 1872. Monducula says, speaking of France, that he finds three notions prevalent among cyclometers: 1. That there is a large reward offered for success. 2. That the longitude problem depends on that success. 3. That the solution is the great end and object of geometry. The same three notions are equally prevalent among the same class in England. No reward has ever been offered by the government of either country. Although from 1714 to 1828 the British government did indeed sponsor a £20,000 prize for finding a solution to the longitude problem, exactly why the connection was made to squaring the circle is not clear. Especially since two non-geometric methods had been found by the late 1760s. De Morgan goes on to say that, the longitude problem in no way depends upon perfect solution. Existing approximations are sufficient to a point of accuracy far beyond what can be wanted. In his book, De Morgan also mentions receiving many threatening letters from would-be circle squarers, accusing him of trying to cheat them out of their prize. Other modern claims even after it had been proved impossible. In 1894, amateur mathematician Edwin J. Goodwin claimed that he had developed a method to square the circle. The technique he developed did not accurately square the circle, and provided an incorrect area of the circle which essentially redefined pi as equal to 3.2. Goodwin then proposed the Indiana Pi Bill and the Indiana state legislature allowing the state to use his method in education without paying royalties to him. The bill passed with no objections in the state house, but the bill was tabled and never voted on in the Senate, amid increasing ridicule from the press. In literature, the problem of squaring the circle has been mentioned by poets such as Dante and Alexander Pope, with varied metaphorical meanings. Its literary use dates back at least to 414 BC, when the play The Birds by Aristophanes was first performed. In it, the character Meton of Athens mentions squaring the circle, possibly to indicate the paradoxical nature of his utopian city. Dante's Paradise Canto XXXII lines 133–135 contain the verses. For Dante, squaring the circle represents a task beyond human comprehension, which he compares to his own inability to comprehend paradise. By 1742, when Alexander Pope published the fourth book of his Dunciad, attempts at circle squaring had come to be seen as wild and fruitless. Similarly, the Gilbert and Sullivan comic opera Princess Ida features a song which satirically lists the impossible goals of the women's university run by the title character, such as finding perpetual motion. One of these goals is, and the circle they will square it some fine day. The sestina, a poetic form first used in the 12th century by Arnaud Daniel, has been said to square the circle in its use of a square number of lines with a circular scheme of 6 repeated words. Spinoza writes that this form invokes a symbolic meaning in which the circle stands for heaven and the square stands for the earth. A similar metaphor was used in Squaring the Circle, a 1908 short story by O. Henry, about a long-running family feud. In the title of this story, the circle represents the natural world, while the square represents the city, the world of man. In James Joyce's novel Ulysses, Leopold Bloom dreams of becoming wealthy by squaring the circle, unaware that the quadrature of the circle had been proved impossible 22 years earlier and that the British government had never offered a reward for its solution. See also, the two other classical problems of antiquity were doubling the cube and trisecting the angle, described in the compass and straightedge article. Unlike squaring the circle, these two problems can be solved by the slightly more powerful construction method of origami, as described at Mathematics of Paper Folding. The Hobbes-Wallace controversy, a 17th-century dispute in the philosophy of mathematics sparked by Hobbes' failed proof of squaring the circle. For a more modern related problem, see Tarski's circle squaring problem. The Indiana Pi Bill, an 1897 attempt in the Indiana state legislature to dictate a solution to the problem by legislative fiat. Squircle, a mathematical shape with properties between those of a square and those of a circle. Squared circle, a professional wrestling ring. References. External links: Squaring the Circle at the Maxshooter History of Mathematics Archive, Squaring the Circle at Cut the Knot, Circle Squaring at Math World, includes information on procedures based on various approximations of pi, Squaring the Circle at Convergence, the Quadrature of the Circle and Hippocrates' Lunes at Convergence, how to unroll a circle pi accurate to 8 decimal places, using straightedge and compass. Squaring the Circle and Other Impossibilities, lecture by Robin Wilson, at Gresham College, January 16, 2008. Grime, James. Squaring the Circle. Numberphil. Brady Heron.